So good evening, Ireland. This is The Science of Santa, a rather tongue-in-cheek talk which will only last a little less than half an hour to give you plenty of time for other festivities at this time of year. So what I'm essentially asking is Santa compatible with the laws of physics? Or to put it the other way round and a little more succinctly, just how many laws of physics does Santa break? Now, we know the story. Santa is allegedly a portly, jolly fellow with a white beard and a penchant for wearing red suits. So, although this does display somewhat questionable fashion sense, that of course doesn't mean that he cannot exist. What about the claims made about what Santa does at this time of year? And we're all familiar with the feats of Santa. He visits all households on Christmas Eve and delivers presents to all qualifying children. And of course, by qualifying, we're referring to the naughty nice list. The question I'm asking this evening is, can we reconcile this? Can we say that Santa does all of these things, but does he do it in such a way that he breaks any laws that we understand? Specifically, is he compatible with our understanding of how science works? In particular, I asked myself when I first thought about this, is there anything that I've said in any of my other talks, and I've given a number of different talks, many of them astro-related, but essentially science-related talks about how the world works or how the universe works. Is there anything that I've covered in any of my other talks that helps us understand how Santa can do what he does? So let's just remind ourselves in one phrase what it is that we're addressing this evening. We're saying that Santa visits households on Christmas Eve to deliver presents to children. We're going to take that phrase, that sentence, and effectively we're going to unpick it one word at a time and ask ourselves, how does he manage to achieve this? So we're going to start with thinking about how many children he actually visits. So we'll start at that end of the sentence. So how many? How many children get presents at Christmas? Well, the Earth's population is approximately 8 billion. Scary but true, it's just past 8 billion people. And amazingly enough, 25% of those people are children. Children in the sense of under 18. Whether or not they still receive Christmas presents, well, that's up to the families in question, of course. But as far as Santa is concerned, 25% of the Earth's population are children, and perhaps half of them are eligible for Christmas presents in the sense that not all households are Christian, and maybe they don't want Santa to deliver presents to their children. So that means at most about 1 billion children get Christmas presents. And of course that does assume the ratio on the naughty nice list. Let's just for the sake of argument assume that all children are on the nice list and no children have found their way onto the naughty list. Parents will tell me that's very unlikely, but just for the purposes of argument, let's assume it's a 0-100 separation of naughty and nice. So we're talking about something of order 1 billion children. So let's pick another word and start dissecting that. Santa visits these billion children. So how does he visit? What's his mode of transport? Well, everybody knows that Santa has a sleigh pulled by reindeer. So the question we can ask ourselves is, well, can reindeer fly? Well, we know that insects fly, and we know that birds fly, and we know that pterosaurs fly. Don't see many of them these days, but they do fly. And of course, there are even some mammals that fly, and reindeer are mammals. But if reindeers can fly, then they apparently choose not to do so for a lot of the time, because we don't tend to see them flying, and I've not seen any photographs of reindeer that are flying. So there is, at the end of the day, very little evidence for flying reindeer. But remember how science works. Absence of evidence is not the same thing as evidence of absence. So just because we haven't got any photographs of reindeer flying doesn't mean they can't fly. It simply means we haven't ever seen them fly. So the jury is out on that particular point. How fast would they have to go in order for Santa to deliver all the presents to all of these children? Well, to visit something of order 1 billion children in one night, which is about 36 hours. Remember, it's not simply the 12 hours, perhaps a little more in the northern hemisphere or a little less in the southern hemisphere. It's not just 12 hours. Santa can use the 24-hour time zones and actually move from one time zone to another. So he actually has something like 36 hours in which to deliver all the presents. In order to visit 1 billion children, we have to make some assumptions as to how those children are distributed across the earth. Of course, they're mainly in the land masses and a lot of them are in cities. But we can do a simple calculation which would tell us that Santa would have to travel at something of order 2,000 kilometers per second to visit that many children in one night. And that sounds like just too much. But as far as the laws of physics are concerned, that's fine. That's not even 1% of the speed of light. And remember, that is the only speed limit in physics, is that nothing can move faster than light can travel in a vacuum. Now, the universe is expanding and space is actually expanding faster than that. But in terms of objects moving through space, nothing can travel faster than light. But Santa would only have to move at less than 1% of the speed of light. So Santa is in no danger of breaking any laws of physics as far as speed is concerned. But wouldn't that make everything rather hot if you move really fast through the atmosphere? Just like a meteor, a small particle, or an asteroid, a larger rock, entering the Earth's atmosphere, when that happens, the air in front of the object gets compressed and heated up. Wouldn't that also happen for the sleigh moving very fast through the Earth's atmosphere? Wouldn't the sleigh get very hot because of the compression of the air? In a different talk, I describe how stars work, and I talk about the ABC of stellar evolution, the ABC of star evolution. And the C of the ABC stands for compression produces heat, because in the center of a star, the gas is compressed, that makes the star hot, and that gives rise to nuclear fusion, which is the power source at the center of every star. So we know that if Santa's sleigh moves fast through the atmosphere, it will tend to get hot. Even if it's aerodynamically designed, you can't get round the problem that the air in front of the sleigh will get compressed and start to heat up. So doesn't that mean that the sleigh will be glowing white hot and will be a really bright light in the sky? Shouldn't that mean that Santa's sleigh is always easy to see, because around Christmas Eve you'll see a bright light flashing across the sky all the time? Well, maybe it was seen. Perhaps that's pushing our luck a bit to say that the Star of Bethlehem might have been Santa's sleigh flying through the air. Given that the Star of Bethlehem was seen before Christ was born, that doesn't seem to fit the right sort of timeline. But other people might seem to say, well, if you're looking for bright lights in the sky, surely we see those all the time. We call them UFOs. Well, maybe we do, maybe we don't. But there is an alternative, because there is a type of matter that we do know about that does not seem to emit or indeed reflect or absorb any form of light. Ordinary matter, when you heat it up, gets hot and starts to radiate light. If you heat something up, if you take a chunk of metal and heat it up, it'll get red hot, and if you heat it up further, it'll get white hot. But not all matter would do that. There's a type of matter out there in the universe called dark matter. We're not actually sure what this stuff is, but we think there's an awful lot of it out there. It looks like there's more dark matter in the universe than there is ordinary matter. And if you take dark matter and heat it up, it does not emit light. And so it would not glow. So maybe Santa and his sleigh, and maybe the reindeer as well, are made of this mysterious dark matter, and that explains why they don't glow when the sleigh goes fast through the Earth's atmosphere. It would also explain why it doesn't show up on radar, because radar is just radio waves, and if dark matter doesn't absorb or reflect radio waves, then it wouldn't show up on radar either. So we wouldn't see it in the sky, and we wouldn't be able to tell it was there. So dark matter is rather mysterious, but then so is Santa in a sense, so maybe they are linked in some way. Let's have another look at that original sentence. Santa visits households on Christmas Eve to deliver presents to children. We've looked at children, we've looked at visits. Now let's think about the households that Santa visits. How can Santa get down so many chimneys? If he's visiting so many children so quickly, how can somebody that, even if he isn't particularly tall, maybe he's somewhat less than 2 meters, maybe he's only 1.5 meters high, how can he squeeze down so many chimneys? He would have to go down thousands of chimneys each second. For somebody that's 1.5 meters high and, let's face it, a little bit portly, a little bit round, there's no way he could squeeze down all these chimneys. So what would he have to do? Well, from our understanding of how the world works, there's a theory called quantum theory, which tells us how things behave on the very small scale. We're all made of atoms, and atoms are made of certain particles called nuclei and electrons. This is described in a talk I give called The Weird World of the Very, Very Small, which says something about how weird things are when you look at the very, very, very small scale of the world. Now, if you were to take a whole load of atoms, such as the atoms that make up Santa, if you could somehow replace the electrons in those atoms with a different particle, a particle called a muon, a bit of a funny name, but it's just another fundamental particle. If you could replace the electrons with muons, muons are a little bit like heavy versions of those same particles' electrons. What would happen is the atom would become 200 times smaller. And anybody that's made of those atoms, if you were to replace the electrons with muons, that person would become 200 times smaller. So instead of Santa being 1.5 meters tall and rather portly, Santa would end up only 1 centimetre or so high, if you could replace all the electrons in Santa with muons. Now, I don't know quite how you would do that, but that's not the point. If you were to do that, Santa would only be 1 centimetre or so high, and he would fit down chimneys very, very easily. So that is a possibility. But you say, these days, not that many houses have chimneys. What if your house or apartment or whatever it is that you live in doesn't have a chimney? How can Santa then get inside? Well, this idea of quantum theory describing how things on small scales work, that comes to our rescue yet again. Because when we look at the atomic world, we see that objects such as small particles can go through barriers, even though those barriers would indicate that, well, it should be impossible for the particle to get through. If that can happen for parts of an atom, then why can't Santa use the same idea? Santa could go from outside a building to inside a building without having to go through any open doors or open windows. He can simply go through, or the word used in quantum theory is tunnel. It doesn't mean taking bricks out of a wall and then going through the gap. Even though the walls are completely solid, it is possible for objects to go through solid objects and appear on the other side. It happens with atoms, it happens all the time with atoms and small objects. Maybe Santa has figured out a way of doing it on a somewhat larger scale. So we've thought about children, we've thought about visits, we've thought about households. He does all of this on Christmas Eve. So how can he do it all in one night? How can Santa make so many deliveries all in one night? If he's travelling at relativistic speeds, in other words, a fair fraction of the speed of light between each delivery, then he would have to do everything in 36 hours. But again, quantum theory tells us that when we look on the very small scale, actually it is possible for particles to be in 2 places at once. Now, that doesn't make any sense as far as we're concerned. It seems to go completely against common sense. If you've got a cup of tea sitting on the table in front of you, that cup of tea is sitting in one place. It can't be at both ends of the table at the same time. But actually, that is the way the world works on the subatomic scale, the scale of atoms or the scale of molecules. It is possible for a particle to be in 2 places at the same time. or indeed 3 places at the same time, or 4 places at the same time. So again, if this is possible for the world of the very, very small, then maybe Santa has figured out a way that he can be in more than one place at a time. So he doesn't necessarily have to visit all of these households one after the other after the other. Maybe he can visit lots of them at the same time. That, of course, would save him an enormous amount of time during those 36 hours. And if perhaps Santa could only be in one place at a time, then he would need an alternative way of making the deliveries in those 36 hours. And again, that is possible because, for instance, we understand the way things work on a large scale, not the scale of atoms, but the scale of planets and stars and galaxies. We know, according to what Einstein tells us about the way the universe works, that matter can distort space and can distort time. So we think we understand how far it is from one point to another. We think we understand how far it is from Manchester to Liverpool or from Liverpool to Dublin. But actually, space can be distorted by the presence of matter. And rather weirdly as well, time can be distorted by the presence of matter. So maybe Santa has figured out a way of manipulating matter in such a way that space and time are changed. We know that this can happen because effectively we see the results of this for very extreme situations, such as very massive stars that end up as mysterious black holes. They can change the way space and time works. We effectively can make observations of these, so we know they exist. Perhaps Santa has also figured out a way of doing it. So we've looked at children, we've looked at visits, we've looked at households, we've looked at Christmas Eve. He delivers presents while he's doing all of this. So if we think about it, we have a bit of a problem. How could Santa carry all of the presents for all of the children as he goes on his way? Assuming that each of these billion children get one present each, how could the sleigh hold that many presents? Well, coming back to what I said just a moment ago, it is possible for the presence of matter to distort the way space and time behave. And when we look at, for instance, black holes, we find that a black hole is a region of space which is bigger on the inside than it is on the outside, just like Doctor Who's TARDIS. Again, this is what Einstein tells us about the way matter changes space and time. So again, maybe Santa has figured out how to warp space in such a way that the inside of his sleigh is actually a lot bigger than the outside of his sleigh, and thus has plenty of space to hold, let's say, 1 billion presents. There's an alternative, which is a bit weird. Well, all of this is a bit weird, but there is an alternative way he could carry all of these presents. And that is, he's not necessarily restricted to the 3 dimensions that we understand. So the 3 dimensions I'm talking about are the 3 dimensions that we can see around us. Front, forward, backward, left, right, up, down. 3 axes that define the 3 dimensions of space. But some physicists, some scientists believe that space is actually made of more than just 3 dimensions. It's only those 3 that we can see. Forward, backward, left, right, up, down. Maybe there's more than just those 3. And perhaps Santa has found some way of using those extra dimensions. So all he has to do is to take the presents, move them from our 3 dimensions into some of these other dimensions, what you sometimes might call a parallel universe, if you want to think of it that way. And then he can go about his business, visit the various children, and then when he visits each household, he simply pulls one of those presents from the other dimensions back into our dimension. Now, again, I really don't understand how he could do that, but there are people who believe that if these dimensions exist, then it might be possible to access them. Personally, I prefer the idea of simply using matter to distort space and time, but if you want to use extra dimensions, well, that's okay as well. So you might say, well, okay, maybe he can do this, but wouldn't it need a huge amount of energy for Santa to do all of this? If he wants to store 1 billion presents, and if he wants to move the sleigh and 1 billion presents at very high speeds, nearly the speed of light or a fraction of the speed of light, surely to do all of this, it would need an absolutely incredible amount of energy. Well, yes, indeed, it would. And if you have a black hole on the sleigh, well, a black hole could provide all the power you need. It is thought, though we haven't actually achieved this yet, it is thought that if you have a spaceship and you have a black hole powering the spaceship, that spaceship could go almost as fast as you like and get you to the next star very, very quickly. So if a black hole could power a starship, then why can't a black hole be used as an energy source in the sleigh? We know black holes exist. We don't know how to put one inside a car or an aircraft or a spacecraft, but maybe Santa and the elves have decided that they can do this. But there's another source of energy that we're overlooking. The elephant in the room, the one thing I haven't been talking about yet. What happens to all the mince pies? Now, nobody is naive enough to think that all the mince pies that are left out for Santa are actually eaten by Santa. That would be just ridiculous. So what happens to all the mince pies? Well, what if Santa could convert the mass of all the mince pies that are left out for him? What if he could convert that mass into energy? Einstein has told us that energy and mass have a sort of equivalence, if you like, an exchange rate. For a given mass, we can work out the equivalent amount of energy, and vice versa, through the famous equation E equals mc squared. E is energy, m is mass. C is the speed of light, which is a fairly big number, so c squared is a very big number. So, could we work out how much energy is available if we make some assumptions about how many mince pies are left out for Santa? Well, I'm a physicist, so I like doing calculations. 1 mince pie is about 50 grams of mass. If we take the 50 grams of mass and multiply by the speed of light squared, we get an energy. And the energy is the number on the right-hand side, 5 times 10 to the power 15 joules. Now, I realise that you don't know what a joule is. A joule is the unit of energy used by physicists, and I'll come back to just how big that is, how big or how small that particular value is. But first, let's work out how much we get for all the mince pies, not just for 1 mince pies. How many mince pies are left out? Well, perhaps not everybody leaves mince pies for Santa. Let's just assume a few % of households leave a mince pie for Santa. So out of the billion, let's take a small percentage of a billion. Let's say 20 million mince pies are left for Santa. So we take the number we've just calculated for 1 mince pie and we multiply by 20 million. The total energy available to Santa is 10 to the power 23 joules, which means nothing to you unless you're a physicist. So let me put that into some sort of context. How much energy is 10 to the power 23 joules? Well, imagine a nuclear power station generating gigawatts of power. And let's imagine that power station doesn't run all night. Let's imagine that power station runs for 1 million years. That's the amount of energy we're talking about. The energy output of a nuclear power station running not overnight, but running for 1 million years. That is 10 to the power 23 joules. And that energy is available if Santa chooses to use it during the night. An absolutely huge amount of energy, easily enough to do all the things I've been talking about. So then you can ask, well, how exactly do you extract that much energy from a mince pie? Yeah, that is a little bit tricky. Perhaps one way of doing it is to take a mince pie and take an anti-mince pie and collide them together in the Large Mince Pie Collider, which is located at CERN. But that begs the question, well, okay, that gives you a huge amount of energy, but where do you get the anti-mince pies from? The mince pies that are made of antimatter. They presumably exist, but nobody leaves these out for Santa, and therefore we have a problem. So you need to find an alternative way of extracting all this energy from a mince pie. Now, you can extract not all of it, but a reasonable fraction of energy from a mince pie via an alternative route. I say most of, it's actually not the majority. You might be able to get 10 or 20 or 30% of the of the energy out of a mince pie by doing what? By dropping it into a black hole. We know that when matter falls into a black hole, an enormous amount of energy is released, because we can see that happening in the distant universe. For instance, during the COVID lockdown, I took an image without using a telescope. I took an image of a very distant galaxy with my camera sitting outside my front door. This distant galaxy goes under the weird name of a quasar. That's simply a type of galaxy with a black hole at its center and matter falling into that black hole, probably not mince pies, probably more like stars falling into that black hole, produce so much energy that this quasar, this galaxy, is visible even though it's on the other side of the observable universe. That gives you an idea of just the huge amount of energy that comes out of galaxies if matter falls into a black hole. It's visible at that distance even without a telescope. So you could say, well, what's the calculation for working out what happens when a mince pie falls into a black hole? Well, I don't know. I can't find any research papers explaining exactly how much energy is released. We can assume it's a very big fraction of the total energy available, not quite as much as you would get from a large mince pie collider, but it's going to be a large fraction of that, even though I can't find any papers that confirm the numbers. Okay, Santa does, in principle, have enough energy at his disposal to do all the wonderful things I've been talking about. But if it's allowed by the laws of physics, but surely how could Santa manipulate space and time in these ways? We know it's possible, but how come he's got the skill set to be able to do that? Well, one thing we have to remember is, at what point do we assume that Santa has to be human? Is it not possible that Santa is a somewhat different person? Remember, nobody's ever seen him. Everybody is asleep when Santa visits, so we don't actually know what he looks like. We don't know whether his skin is green or not. So, when it comes to this question, just how many laws of physics does Santa break? I think when you sit down and think about it all, the answer is none. So feel free, everybody, to draw your own conclusions about the existence of the portly, jolly fellow with the white beard and the penchant for wearing red suits. Regardless of what conclusion you come to, may I wish you all a very Merry Christmas. Thank you all for listening.